Hello, my name is Ryan Brown. My partner is Tiernan Barber. This project is called WINEO. It is an enhanced fuzzing technique for Windows executables that uses a version of Wine that implements a Forkserver to increase the efficiency and speed of fuzzing Windows text editors in a Linux environment. Here's what we'll cover today. First, we'll introduce fuzzing and why it's important. Then we'll explore the problems of fuzzing on Windows, followed by an overview of existing solutions. Then we'll get into the methodology of our approach and the implementation of the Forkserver. After that, we'll share the results for the text editors that we chose, discuss the challenges that we ran into, and then wrap up with our conclusion. Let's start with fuzzing. Fuzzing is a method of automated testing where we feed random or mutated inputs to a program to find bugs. These bugs could be crashes, vulnerabilities, or memory leaks. Think of it as stress testing software. For example, we might send a malformed text file to a text editor to see if it crashes. This diagram here shows the 5 steps in the fuzzing process. The fuzzer generates the inputs, runs the program, analyzes the behavior of the program, and then determines if there were any issues. Fuzzing is widely used by many tech companies or any company really that develops their own software, and it's critical for security. So where's the problem? Fuzzing is a powerful tool, but it's far less effective on Windows, which holds over 70% of the desktop market. Linux has been increasing their market share over the last couple of decades, but as you can see, it is still way below that of Windows. That being the case, a lot of applications are developed for Windows that aren't readily available on Linux. Another issue is that many Windows applications use a graphical user interface, otherwise known as a GUI, and aren't developed with a focus on running them in the command line. This makes fuzzing a majority of Windows programs extremely difficult, requiring detailed knowledge of the internal libraries of a program, which is usually unavailable for closed source applications. Unlike Linux, Windows doesn't have a fork system call for fast process creation as well. Instead, it uses the create process function, which is slow because it builds a whole new process from scratch without copy on write efficiency, which I'll explain in the next slide. As you can see from the graph in the bottom right, the time it takes to create a process on Windows is considerably longer than that of Linux. So with that, we get a much longer duration to complete fuzz testing on Windows in a much less efficient manner. To understand where our project fits, let's look at some existing fuzzing tools. The first one is AFL. AFL runs on Linux and is incredibly fast, hitting thousands of inputs per second. It does that by using the fork system call with copy on write. As shown here, copy on write is a technique used in Linux where when a child process is created, it shares the parent's memory, the code, data, everything, without copying up front. Only if the child process modifies something does it make a copy of that specific memory location. This makes the process creation very efficient and usually only takes microseconds. The next fuzzer we'll look at is WinAFL. WinAFL on Windows is open source, but is much slower than AFL on Linux. It relies on the create process function, which is far less efficient and takes considerably more time than the fork system call on Linux. For each fuzzing input, the create process function creates a whole new process from scratch. So it has to load the executable, allocate the memory, set up threads, and initialize resources. So when fuzzing a program using thousands of inputs, this method is very resource heavy and takes up a lot of time. These new processes don't share any memory, so with every new process created, it just continues to eat up memory. And if you don't have a high-end workstation that is built for this type of testing, you can quickly run out of memory and freeze up your computer.
So here's a very interesting approach to fuzzing on Windows. Instead of running the entire process start to finish after a create process call, we can simply target the functions we want to invoke only. Now, this might be difficult for closed source applications. You might ask, like, how can you possibly find functions that you could even mutate for fuzzing? Well, Winnie does this automatically, which is incredibly impressive. It creates little harnesses, which are programs that specifically target those memory related functions. It finds memory related functions by creating a map of all of the dependencies of each function. It finds execution traces of the binaries. It sees the binaries themselves. It sees all the APIs involved, especially memory related APIs like OpenFile and ReadFile. It can even find pointers by running the program multiple times and seeing which arguments randomly change. So this is 30 times faster than WinAFL and more effective because out of the 59 executables tested, WinAFL could only immediately run 30 of them, whereas Winnie, with a few modifications very slight to the harnesses, was able to run all 59. So on Linux, we can fuzz Linux applications. We can use AFL. We can also do uh, harness generation with Fudge and FuzzGen and some other similar programs. We can fuzz Windows programs on Windows. We can use WinAFL. We can use Winnie, as just discussed. We can also use the Windows subsystem for Linux to use open source Linux fuzzers as well. Now, is the vice versa true? Can we fuzz Windows executables on Linux? That's the question. So, our goal in this project is to do just that, to implement a Forkserver in Wine so that we can use efficient Linux style fuzzing for Windows executables anywhere on any Unix system. We specifically target Notepad, Notepad++, Sublime Text, and Vim as the text editors we will test for this fuzzing process. Here's a little background that's necessary for understanding here. Wine is not an emulator. That is the official name, or at least was. The What it does is it translates API calls from Windows system calls to Unix system calls. It uses a middleman called POSIX, which is the Portable Operating System Interface. It's an IEEE standard. And instead of doing what an emulator normally does, which is translate assembly code from one system to another, it just takes API calls for the two systems. Fork is a very important call, as discussed already. Uh, it duplicates processes, including all of their memory, and it is memory efficient because it only duplicates that memory when the memory is written to by the child process. A fork server is important because it gets rid of the overhead of resetting the process every time. You make a fork server start right before you want to mutate the function. So instead of uh, running through the wine setup every time, we're going to have a fork server start after the wine loading and starting up has done, right before it calls the initialization of the Windows program. This will greatly improve efficiency, as we're about to see. So our methodology is to test a fuzzer and that we build against Windows X. We're going to use the same fuzzer and modified wine. Then we're going to use a slightly modified wine with a fork server and see if the fuzzer improves its efficiency there.
For the benchmarks, as mentioned before, we chose 4 Windows text editors: Notepad, Notepad++, Sublime Text, and Vim. Why did we choose text editors? Because they're very common, they have a good range of complexity between them, and they can all be run from the command line and accept file names as arguments. This made them easy candidates for creating mutations from the seed input and then testing each of those mutations. The ones we chose all have a portable Windows version available, meaning they don't have to be installed anywhere and can be run from wherever as long as the dependencies are in the same folder. This made it easy to move them over and run them in the Linux virtual machine. Notepad is actually included with the Wine install, so we didn't even have to worry about that one. For the fuzzing executable to test the text editors in Windows, we went with a very simple approach written in C++. And all it does is take this seed file and it randomly selects between 1 and 10 random bytes, flips them, and then attempts to open up the text editor with the mutated input. It does this 500 times for each text editor, the only exception being Vim. When we tried 500 inputs, the computer would crash after about 230 files. Vim opens up a whole new window when a new file is opened up, unlike Sublime or Notepad++ that show all the open files as tabs within the same window. We believe this attributed to us running out of memory and the computer just locking up. For the Forkserver implementation on the Linux side, we ported the fuzzer to be a Linux binary and adjusted it so that instead of directly opening up the text editor, It would send the mutated input to the Forkserver's standard input, which would then trigger it to fork a new process.
So, implementing the fork server was a bit of a uh, tough question. We found that there are two sides of the program loader. There's a Windows side and a Unix side, and the system calls in each are specific to each system. Um, the one in the Unix folder is the one we eventually targeted because it allows us to use fork directly and not have to worry about any translation back to Windows API calls within that file. And it allows us to read and write from the buffer directly. By only using one wine process for all the test cases, we greatly reduce the overhead of testing with the fuzzer on wine. Here's a little bit of a pseudocode for the algorithm that runs the Forkserver logic. We created a new environment variable wine Forkserver that would only allow this code to run if the environment variable was set by the user. Then we read from the memory buffer and see if there's a signal that says we want to do some fuzzing. And if so, we continue. We create a child with a fork, and then we check, is this process itself a child with no children of its own? If that is true, then we unset the environment variable and continue running. And right after this block, there is already memory copy functions. So I didn't have to manually implement um, any additional memory management, which was very convenient. Fork handled the first half, and then the program itself already had mem copy instructions specific to the wine setup. And so if the process has more than one child, it waits for the child to collect the status, and then it finally continues by itself.
To run our experiment, we compiled and ran the fuzzer on a Windows 10 computer with a 6-core AMD CPU with 32 gigabytes of RAM. For the Linux tests, we ran it on the same Windows computer in a virtual machine on Oracle VirtualBox. The VM was running Ubuntu 22.04 and was set up to use 6 cores and 16 gigabytes of RAM. Now I'm going to demonstrate fuzzing one of the editors with the Wine Forkserver. Okay, here's a quick run through of our main function in the fuzzing application. First, we just create the two pipes for communication, writing to the Forkserver standard input, reading from its standard output. Then fork a child process to start wine with the Forkserver, pass in a temporary file name. The child then exits. The parent sleeps for 2 seconds, waits for the Forkserver to initialize. Then it closes the unused pipe ends for the communication. And here's where it starts the loop for however many inputs we put in. Mutates the seed input, writes that input to a temporary file in the temp directory, and then sends a byte to the standard input of the Forkserver to let it know it needs to fork a new child process for that temporary file. I'll then added a delay in there so that because we're run into a race condition, and then we wait until we see something from the Forkserver again, signaling that it's ready for another input. And then it just keeps looping through until it's finished. And then we just close the communication pipes, clean up the memory, and have these outputs for the elapsed time and the input rate. I'm going to run the fuzzer on the Sublime text editor. We tried to run them all together in one executable, but it was locking up the system, so we decided to just recompile the fuzzer with each text editor separately, so that we didn't run into that issue anymore. So I'll just kick it off here. I added some printouts so that we could see when a new process was being forked, so we can see that's happening 500 times. There, the fuzzer shows as completed, finishing in 5.78 seconds. But it does take a minute for the window to come up, So I'm going to pause the recording and pick up again when the window is up. All right, so now we've got the Sublime window open. Wine has successfully opened up all 500 files, all with random mutations of the same seed input. We haven't detected any bugs or crashes, but we've proven that fuzzing these Windows programs in Wine with a Forkserver implementation can drastically speed up the testing. Okay, now for the results. The first text editor we tested was Notepad. This ended up being tied for slowest on the Windows benchmark, completing 500 iterations in 501.53 seconds, which gave us an input rate of about 1 input per second. Notepad, like Vim, opens up a new window for each text file that is opened. We believe that's partly to blame for the slow execution rate on Windows. We then tested it with an unmodified Wine build on the Linux virtual machine, and it was slightly slower than on Windows, probably due to the extra overhead of mapping the Windows to Linux API calls. It completed 500 iterations in about 521 seconds, giving us an input rate of 0.96 inputs per second. Running the fuzzer in Wine with the Forkserver was a huge upgrade, completing 500 iterations in just over 5 seconds, giving us an input rate of 98.4 inputs per second. We weren't sure how much of an upgrade to expect with the Forkserver, but we were not expecting a 100 times improvement. This was obviously way faster than running in Windows. Next, we tested Notepad++. On Windows, it completed 500 iterations in about 129 seconds, giving us an input rate of 3.88 inputs per second. Notepad++ opens up all open files as tabs in one window, so we think that attributed to the increased rate over Notepad. Running in Linux with unmodified Wine, however, it was much slower, completing 500 iterations in 842.9 seconds, giving us an input rate of just 0.59 inputs per second. Running in Wine with our Forkserver was another huge improvement, completing 500 iterations in 6.25 seconds, giving us a final input rate of 79.98 inputs per second. Next, we tested Sublime Text. This was the fastest one on Windows, completing 500 iterations in only 41.82 seconds, giving us an input rate of 11.96 inputs per second. Sublime is another editor that has all the open files in tabs on a single window, likely contributing to the faster iterations on Windows, like Notepad++. However, it was still much slower with Wine, on the other hand, completing 500 iterations in 644.08 seconds, giving us an input rate of only 0.78 inputs per second. Running with the Wine Forkserver completed the 500 iterations in only 5.48 seconds, giving us a final input rate of 91.926 inputs per second. Finally, we tested Vim. Vim was tied for slowest along with Notepad on Windows. Like Notepad, Vim also only has one window open per file, so no tabs like Sublime and Notepad++. With the truncated test of only 200 iterations, it completed in 201.88 seconds, giving us an input rate of 0.99 inputs per second. On Linux using Wine, it followed the trend of being much slower this way, completing the 200 iterations in 607.25 seconds, giving us an input rate of 0.33 inputs per second. Rounding out the Forkserver tests, this was another huge improvement, completing 200 iterations in 2.42 seconds, giving us a final input rate of 82.6 inputs per second. Overall, we saw huge improvements with all text editors running in Wine with the Forkserver. Notepad++ saw the largest decrease in total time to completion, where Vim saw the largest rate increase. This proves that running a Forkserver in Wine can drastically increase the rate that you can fuzz test Windows executables.
So we had some challenges with this setup. Um, Just like Windows, there's 32-bit and 64-bit environments, and they have different dependencies. And so to avoid any possible confusion, we simply stuck to 64-bit wine for this experiment. The how to communicate with the fuzzer was an open question. While we ended up using memory buffer, we are aware that this poses a possible security vulnerability because the memory buffer can be read and written to by other processes on the system. So at the very least, for a commercial release of something like this, we would want some level of encryption, if not use some other system for communication. The latest version of Wine had some missing header issues. The auto configure script was failing to set a lot of the environment variables and for include guards. So you would end up with a have X file variable not being set, and so that file would not be found when it came time to compile. And I was trying to manually fix these, but eventually we realized that it would just be so much less of a hassle to use a stable version than try to fix the auto configure script ourselves. So Wine additionally looks for hardware because it's trying to emulate all of Windows's functions, or trying to approximate, not emulate. Wine is not an emulator, but it's trying to approximate the hardware. So it would look for headers like cd-rom.h, which the Windows subsystem for Linux doesn't have those headers. And eventually, if you try to build your own modified Wine, at least for version 10 on WSL, you're going to run into these files just won't be found. And you can turn off some of them with flags that disable graphics and such, but it became very evident that just using a virtual machine or natively running it would be much more smooth. Our fuzzer, also, we had a question of whether we want to wait for the GUI to load before we continue with the next fuzzing instance. And because the GUI loading time fluctuated so wildly, we decided to simply count the fuzzing time and not the time it takes for the windows to load. And that is what we used in our report. And we also needed to know how to mutate input. And that's kind of an open question for things that aren't text editors, where you could just put in random strings, such as ffmpeg and 7-zip. But first, let's talk about the differences here between Wine with the Forkserver and WINEO. Theoretically, you could implement WINEO within our Wine Forkserver as well. But effectively, we are forking right before the Windows program starts. So it's similar to WinAFL in the fact that you're running the whole program, you're not generating a harness, and what overhead is removed is the Wine overhead, not any of the Windows overhead specific. We could have injected a fuzzer into the Windows loader as we attempted at first, but recognized it would be very program specific and a bit more of a technical challenge. So for the sake of demonstration, we used the Unix loader, but future work would likely see if we can implement that in the Windows side and do some API translation there. So application-specific mutations might be necessary for video encoders or zip file preparation software. And so in addition to changing the arguments, you also need to have a lot of random files made and ready if you really want the fuzzing to be to cover all possible edge cases. And so we explored a little bit with that, but ultimately had time for the text editors. So that's what we went with, but future work would likely explore how to make sure all possible arguments were fed into ffmpeg and all possible tests were run at a quick rate. So Fork already has some built-in parallelism, but we could also use asynchronous returns and improve the efficiency of the Forkserver. We could limit the amount of children used because we actually ran into a problem with the VM running out of memory. At first, we had to increase the memory, but it's not always going to be the case that you have more. And so to make this universally available, we might want to limit the resource usage somehow or auto-moderate it. And we could also, as discussed before, preload part of the Windows application in the other loader before we fork. So, in conclusion, we have effectively implemented a fork server in Wine to perform fuzzing of Windows programs on Unix. It is incredibly effective and fast compared to just fuzzing with Windows fuzzers through Wine, and shows that in addition to Wine's stated purpose of importing Windows programs to the Unix platform for compatibility's sake, it can also be used to extend technical capabilities to those programs, especially for testing. Windows programs historically pose a difficult but not impossible challenge for fuzzing. As we saw with WINEO, breakthroughs on Windows natively are able to auto detect entry points for possible fuzzing mutations and allows for a future where closed source programs are no less testable than open source programs. And WINEO successfully detected many of previously unknown issues in these programs and shows that fuzzing continues to be an effective debugging tool. Throughout this entire project, the differences between the Windows System API and Unix System API were on full display. Processes like fork or functions like fork are very effective for efficiency because they copy the entire state of a running program, while as create process simply starts a new process and the entire execution trace has to be run again. So this field continues to be interesting. Fuzzing continues to be effective and an important tool in debugging, and the Forkserver in Wine is just the first step towards future exploration of fuzzing Windows programs on Unix. That is everything. Thank you.